resume lecture 2.
Okay, I hope that was a long enough break for you. Okay, so what we discussed so far was a bit high level, right? Because we didn't really talk about the actual gates. So at the end of the day, we will talk about quantum algorithms. And I just said that these constants don't matter too much when it comes down to studying the complexity of the algorithms. But and indeed, for most of the course, I will focus on that. I'll focus on the big O notations. But I thought I should at least tell you about how people think about gates, because there are some choices which, if you look at the papers, it won't be totally obvious. And so in this lecture, I want to tell you about how I think about what kind of gates are more expensive, more cheap, more difficult, easier, that kind of things. Okay, so in the classical world, I told you that there are these NAND gates, and I said they are universal. And what I meant by that was that any classical computation can be broken down into a sequence of NAND gates. So anything that you want to do, you can you write down a sequence of NAND gates and you can express it that way. In quantum computers, the state space is, of course, this tensor product of two-dimensional hyperspaces. And the most general unitary operation that you can apply on this space is obviously a general element of the unitary group. Okay, and so in some sense, you can think of the set of all unitaries in this 2 to the n dimensional hyperspace as a space of all possible quantum computations. And so the question that I want to address is how can we actually, is there a universal gate set in a sense that you can implement any unitary operation? You can synthesize any unitary operation from a sequence of gates in the universal gate set. And the claim is that if you can apply any single qubit gate and any two qubit gate, then this will be sufficient to generate the entire universal gate set. So we've already talked about the single qubit gates. We use the standard basis, and it's just a 2x2 unitary matrix. And of course, there are all sorts of single qubit gates you can consider, but in quantum computing, a very useful set of single qubit gates are the Pauli operators. You may know these as sigma x, sigma y, and sigma z. They're exactly the same as these, but in quantum computing, they're used very often. So instead of writing down sigmas, they just write everything down as x, y, and z. And because these are Hermitian operators, obviously we can exponentiate them. And these will be, again, unitary operators. So these are the single qubit gates people typically think about. What about the two qubit gates? Two qubit gates are just 4x4 matrices because this acts on 2 qubits, and the hyperspace of 2 qubits is 4-dimensional. And there are, again, the gates that people typically consider. The example and the most prominent examples are the C0 gates and CZ gates. So how do they behave? So we can specify them by considering their action on the basis set. So I'll just do that. So under C naught, these basis states transform as follows. And I should say this is actually not symmetric under the exchange of the two qubits. So you can see that there are two indices here. And if we have C naught 1, 2, in words, we say that we have a C naught from 1 to 2. Here, 1 and 2 are qubit indices. And the way to think about this is the following. So 1 is called as the control qubit, and 2 is called as the target qubits. And the way this works is that you look at the control qubit, and if it's 0, you do nothing. And if it's 1, you apply the NOT gate. So on the second qubit. So what is the NOT gate? It just changes 0 to 1 and 1 to 0. And indeed, if you look at this lookup table, well, if the first qubit is 0, then you do nothing on the second qubit. If the first qubit is 1, you simply flip the second qubit. Okay. And people will often draw a circuit diagram like this to represent this guy. And this little dot, this is means that this is a control qubit, and this I don't know how to call this shape thing. This is usually the target. Okay, and the CZ gate is very similar, except that you control on one of the qubits, and you don't apply a NOT operation. You apply a Pauli Z operation. So what is this Pauli Z operation? It's simply a phase operation. It's right here. So if your state is in the 0 state, you do nothing. And if your state is in the 1 state, then you apply a phase of -1. And for now, I'll just follow the same convention as CX, C naught gate, and say CZ 1, 2. But we'll later see that there's something different about the CZ gate compared to the C naught gate. So according to this rule, we look at qubit number 1, and only if it's 1, you apply the Z gate to the second qubit. So we only need to look at these two possibilities. And if you apply the Z gate to the second qubit when the second qubit is in the 0 state, you do nothing. You accumulate a trivial phase. But in the second case, you get this phase, because if it's 1, you apply the Z gate to the 1 state, then you accumulate the phase of -1.
Question?
Yes.
So obviously CZ is only meaningful operation in the quantum system, whereas C
right. Yes.
is both classical and quantumly meaningful operations.
Mm-hmm.
Okay.
That's right. Yes. So if you have a single, so if you're not in a superposition, CZ gate will act trivially. Yes. Yeah. And another interesting difference between the C naught gate and CZ gate is that CZ gate is actually symmetric under the exchange of the two qubits. Well, you can clearly see this from this table. And so even though I wrote this down as CZ 1, 2, this is clearly equal to CZ 2, 1. So sometimes people will not even write down the qubits that these things act on when those qubits are obvious, because the ordering doesn't matter. And we write that down as by this symmetric diagram. So this is a CZ gate. And we have n-qubit gates. Well, these are like, well, these are in principle, this can be like any unitary operator acting on the entire Hilbert space. But there's a very useful set of operators called as Pauli product operators. These are simply tensor product of Pauli operators, where P1 Pn is either identity, X, or Y, or Z, up to a global phase. And of course, this is just a very special case of the n-qubit gates, but it's something that appears quite often. Okay. So we were, just to get back to the original context, we were talking about the universality. So in the classical case, the NAND gates are universal. And in the quantum case, I said that the 1-qubit gates and 2-qubit gates are universal. And the way you can show this is pretty straightforward. I will only give you a sketch of the main idea. The idea is the following. To show universality, it suffices to show that you can generate this operator for any Hermitian operator, where with an infinitesimally small time, because any unitary can be really broken down into so any unitary can be simply written down like this, where this is just an integer. So, and by making delta t very, very small, you can expand this exponential of IH delta t. And the idea is the following. So given an arbitrary Hamiltonian H, it turns out that you can always decompose that into a sum of these Pauli product operators. So alpha pp, where this p is a Pauli product operator, and alpha p is a real function. Okay. And this simply follows from the fact that these Pauli product operators form a basis of the set of operators. So without loss of generality, any operator you can expand in terms of these Pauli product operators. So then you can see well, how this roughly works. What you do is that you decompose this exponential of IH delta t into roughly I alpha p delta t p over p. And of course, all these terms, they don't generally commute with each other, but in the limit that delta t goes to 0, this equation is approximately true. And so what you actually only need to show is whether you can implement operation like this. P delta t p. And alpha p and delta t together, this is just a very small constant. So how do you do that? I will not show you how to do this, but later, I mean, even later, I'll just like state this fact. But later, I will claim that any Pauli product operator can be written as U X like this, where U is a unitary operator, which is a sequence of C naught, CZ, sorry, not CZ, C naught, and a single qubit operator is called Hadamard operator, and another single qubit operator called the phase operator. So the point is, this P can be broken down into a unitary, which is a sequence of two qubit and single qubit operators. And this is also a single qubit operator. This is again a sequence of two qubit and single qubit operators. So this thing can be again written as a sequence of single and two qubit operators. Therefore, any quantum computation, it can be broken down into a sequence of two single qubit operators. So in that sense, single and two qubit operators, unitary operators, they're universal. So that's all great. And in fact, in experiments, now you can implement 1 and 2 qubit gates in pretty much any quantum technology that is out there. But that's really not the end of the story, because so the thing that I want to focus on here is what kind of gates are we going to actually use? And these single and two qubit gates, they are universal for the purpose of synthesizing a arbitrary unitary operator in this large dimensional Hilbert space, but they have some problems in real life. And that problem is noise. So in real experiments, so these gates we can write down mathematically precisely, but for instance, if we apply a Pauli gate, like in practice, it won't work exactly like that. I mean, there will be some maybe over rotation, some decoherence, some kind of noise. And currently the best noise rate is between, let's say, 10 to minus and 10 to minus 2. I guess sometimes you can say 10 to minus 4-ish, but that's somewhat isolated examples. And this means that we cannot run a long combination and hope to get a correct result. So if we have a noise rate of, let's say 10 to minus 3, and if we run like 1,000 gates, probably at least one error would have occurred during the computation, and that error could potentially mess up the result of your computation. So that's a problem. And maybe that wouldn't have been a problem if there are useful quantum algorithms that uses a small number of gates, like maybe I don't know, 100 gates or something like that. But the fact of the matter is, even the best, by best, I mean the quantum algorithm that's supposed to be useful and also uses a smallest number amount of gates, even those algorithms tend to require at least like 10 to the 8 to 10 to the 9 gates. It's quite a substantially larger number than 10 to the 2 or 10 to the 3. So probably if you run this many gates with an error rate of 10 to minus 3, with basically probability 1, you'll get an incorrect result. And to get a correct result with high probability, the error rate will probably have to be much smaller than 10 to minus or 10 to minus 8 or 10 to minus 9. And the current consensus is that we won't be able to achieve that without doing something called as quantum error correction. And I will not talk about quantum error correction in this course because that's a huge subject. But the reason why I'm talking about this is because once you accept that for useful quantum algorithms that you need quantum error correction, this significantly constrains the gates that you can actually use. So that's the main point that I want to get to. So quantum error correction, whatever it is, it's some scheme that can reduce the error. Okay? And that's one of the reasons why people still think that it is possible to build a large-scale quantum computer. But if you start to use it, then there are some very fundamental theorems about quantum error correction, which forbids you from using certain gate sets. For example, you might think that this gate like this, exponential of I theta z, so remember z is just this 2x2 matrix, is compatible with error correction. So you might think that this is a very simple operation, like a single qubit gate. You just simply turn on a magnetic field in the z direction for a spin 1/2 particle, and that's it for a short time. It turns out that gates like this is actually incompatible with quantum error correction. And people have actually shown that, so what these folks have shown that is that if you have a quantum error correction scheme that can implement these kinds of gates in a very straightforward way, I can explain about that more if you're interested, but straightforward way, then the underlying quantum error correcting code, it cannot correct any error whatsoever. So it's completely useless for the purpose of quantum error correction. So the point of all of this is that the set of gates that you can actually implement while doing error correction is highly constrained. And the gates that people use in the literature are precisely these gates. So one good news is that fortunately, there is actually even though the gate set is not is more restricted, it is still universal in the sense that any quantum computation can be still implemented by a sequence of fault-tolerant single and two-qubit gates. And this is actually a discrete set of gates, meaning that the gate set is not continuous; it's finite, but still that is okay because it's still universal. And there are different choices, but these two really stand out. One is called Clifford plus T, and the other is called Hadamard plus Toffoli. Toffoli is the thing that we talked about before, and Clifford plus T, we'll talk about it soon enough. Okay.
So
yes.
the thing that sort of confuses me about this sort of statement is that clearly some unitary operations are continuous, like this unitary rotation by the Pauli matrix, which you said is not susceptible to quantum error correction. But then you're listing these fault-tolerant quantum gates that are supposed to be universal. But you're simply not able to mimic these continuous unitary operations in terms of these discrete operations. So,
so maybe actually the next slide does talk about that. So,
okay.
Yeah. So, well, how should I say this? So I guess there are two questions. So, two parts to this. One is, can you approximate an arbitrary, let's say, I think the simplest question is this: can you approximate arbitrary single qubit unitary operation by a from a discrete set? And the answer is actually yes. So actually, let me go back to the previous slide. So for a single qubit, unitarity, it is known that let's say we have two gates, H and T, where H is a 2x2 matrix, and T is again a 2x2 matrix. Both are unitary operations. Then so this gate set is universal in the sense that any 2 by 2 unitary U can be approximated with error less than epsilon using order log 1 over epsilon h and t gates. So this is a known fact. So I guess we can learn at least one thing from here, which is that any you can actually approximate a continuous gate set arbitrarily well using a discrete gate set. However, it's not like you can it's not like you can exactly implement all the gates exactly in a finite sequence. But for all intents and purposes, we can make this approximation error very small, and the cost that you pay only grows logarithmically with epsilon. So it's a reasonable cost. So you can implement arbitrary you can approximate arbitrary single qubit gates this way, and a similar statement holds for 2-qubit gates as well. So then the statement for this universal quantum computation is that it's not that you can exactly synthesize arbitrary unitary operation from a finite sequence of these gates, but rather you have some approximation error, and you can choose a sequence such that you can make this approximation error arbitrarily small.
So are you saying that you can apply a very long sequence of H and T operations like H, T, H, etc., so that it mimics any unitary matrix with as much accuracy as you want?
Right, that's right.
Oh, I see.
Okay, right. And moreover, it's if you actually want to run these algorithms, just knowing that this is possible in principle is not enough. You given, let's say I have this problem. So I wrote down my quantum algorithm, and I need to use this I need to use this gate U ABCD, where ABCD are some numbers, and I want to be able to approximate this U up to an error of epsilon using H and T. So how do I do that? So it's not obvious how one can do that. And fortunately, that problem is also solved. So not only we can not only ensure the existence of that sequence, we can actually find the sequence that gives that kind of approximation. So in that sense, for all intents and purposes, when you design a quantum algorithm, you can just sort of assume that you can apply any single and 2-qubit gates, because even though down the road those will need to be translated into sequence of these H and T gates, that part of the problem is solved already. Okay, so I briefly mentioned about Clifford gates. So what are the Clifford gates? So their definition is the following. So they are unitaries such that if you conjugate the Pauli product operator by these unitaries, you again get a Pauli product operator. So it's a it's basically unitary. It's a group of unitary operators which preserves the Pauli product operators up to a global phase. And what is known is that this Clifford group is actually generated by these three elements, H, S, and C naught. So H already told you what that is. It's just a 2x2 matrix. S is what is called as phase gate. And I forgot, H is called as Hadamard gate. And C naught already told you, so I won't write it down again. And just to revisit what we discussed briefly in the beginning, so I had this like a rough sketch of the proof for the universality of single and two qubit gates. And I mean, for any operator, gates of this form can be implemented by a sequence of single and two qubit gates. And this is possible because the Clifford groups preserve the Pauli product operators. There should exist a Clifford unitary, let's say U, such that if you conjugate some single qubit operator, like Z tensor identity by U, you end up getting P. So these two are the same. So there should be a U, which is a Clifford, such that this is true. And there's a simple formula that we all know and love from quantum mechanics. And it's that if we have this unitary in the exponent conjugating something in the middle, then we can pull out that unitary. And Clifford, they can be generated by single qubit gates and two qubit gates. And its inverse can be also generated by single qubit gates and two qubit gates. And what's in the middle here, so that's obviously a single qubit gate because it acts only non-trivially on the first qubit. Therefore, this entire thing, this is a sequence of single and two qubit gates. Okay, and in the context of fault-tolerant quantum computers, Clifford gates are cheap, so to speak. So these can be thought as perhaps the cheapest non-trivial gates. I mean, there are even cheaper gates, such as the Pauli gates, but I'm not going to discuss that today. For the purpose of today's lecture, think of Clifford gates as like the cheapest possible fault-tolerant quantum, non-trivial quantum gate that you can implement on fault-tolerant quantum computer. But unfortunately, well, okay. So it turns out that Clifford gates are theoretically interesting, but they have some deficiencies. And the main deficiency is that if you only apply Clifford gates to a simple initial state like the all product state over all zero, then the entire quantum computation can be actually classically simulated. So this does not mean that arbitrary quantum computation can be simulated classically, because Clifford gates are a very specific subset of the circuits that you can implement. But what it does tell you is that if you only have if you only apply Clifford gates, probably that's not gonna be very useful for achieving quantum speedups, because whatever you're doing, you can just classically simulate. So to utilize the full power of quantum computation, you actually need gates that are outside of the Clifford group. And these are called as, obviously, non-Clifford gates. And the examples of non-Clifford gates are many. There are many such gates. But as before, the set of non-Clifford gates that is compatible with the with fault-tolerant quantum error corrected fault-tolerant quantum computation is highly restricted. And one of the few examples that you can actually implement are T-gates or Toffoli gates. So T-gate is, again, this guy. And Toffoli gate, well, we've already talked about it, so I'm not going to repeat it again. And the key point is that when you read all these papers about quantum algorithms, like many times they will talk about the non-Clifford gate cost, such as the T-gate cost or the Toffoli gate cost. And this is usually the number of T-gates that you use or number of Toffoli gates that you use, and et cetera, et cetera. And this is a good figure of merit to understand the real world cost of quantum algorithms, because non-Clifford gates are vastly more expensive than Clifford gates. So they are much slower. And also they require more qubits to actually implement. So almost always, except for maybe some pathological examples, counterexamples, the cost of the quantum algorithm is really determined by the number of non-Clifford gates, at least when it comes down to the time complexity of the algorithm. So it's important to distinguish between the number of gates, number of Clifford gates, and number of non-Clifford gates. And there's another class of gates that are often used because it's quite intuitive. And those are the rotation gates. So these gates are of this form. So exponential of I theta z. So without error correction, this seems like the simplest thing that you can do because, as I said, you can just turn on an external magnetic field and that's it. But as I said, in fault-tolerant quantum computer, this is actually not trivial to implement. There's good news and bad news. The good news is that at this point, there's a near optimal solution to this problem, meaning that given an arbitrary real number of data, and let's say I want to implement this exponential of I theta z using Clifford gates and non-Clifford gates, and I try to minimize the number of non-Clifford gates, then under some number theoretic assumptions, which seems to be correct, you can actually find the optimal solution. You can find a sequence of gates that approximates this guy to the precision that you want in an optimal way. So this was done by these two folks. It's a very important result. And they actually, on average, in the worst case, in the worst case, actually, and also on average, the number of T-gates that you end up using is 3 log 1 over epsilon. And just to remind you, you could have written this as 3 log 1 over epsilon plus something like this, because log 1 over epsilon scales much slower than log 1 over epsilon. And this is optimal. So that's the good news. The fact that you can actually find this sequence and in an optimal way is the good news. The bad news is that in practice, when you put in a realistic numbers for practical quantum algorithms, let's say if you want an error precision of 10 to the minus 10, okay, then if you plug in epsilon to epsilon equals 10 to the minus 10, you get roughly 100 T-gates. So T-gates are non-Clifford gates, so these are already expensive things. And this is saying that if you want to implement rotations, it's actually even more expensive, almost by 100-fold. So you can see that in the fault-tolerant quantum computing world, the cost of different gates is quite counterintuitive, because Clifford gates, so these things include things like C0 or CZ, well, it also includes H and S, But the important thing is these are 2-qubit gates. And in the experiments right now, the 2-qubit gates are the harder gates to implement. Single-qubit gates are extremely good. People can sometimes achieve an error rate of 10 to minus like 5, which is amazing. But the 2-qubit gates, they are slower. They are more error prone. So those things are the harder ones to implement. And it looks like these T gates and rotations, even though they are like they are single qubit gates in the fault-tolerant world, somehow the cost to implement them is much larger than these Clifford gates. And you can see that there's a clear difference in the order of magnitude. So this is why when we, as we'll see down the road, you'll see examples in which when you can use rotations, they instead use things like Toffoli gates or doing integer additions. And you also see that the papers are written in such a way that they try to minimize the T gates, and in particular the rotations. And this is the basic reason why that's happening.
But wouldn't it be the correct impression that if you try to solve some Schrodinger equation type problem on a quantum computer, then doing the rotations is everything?
So I think around sometime between 2015 and 2020, I think people began to realize that that's no longer true in some sense. So that seems like the most obvious thing to do, but I think it's fair to say that now, well, okay, so we will still be interested in implementing this unitary evolution generated by some Hamiltonian. However, the way to implement that rotation, so the naive way is to do these like actual single qubit rotations, but there are better ways, and those better ways try to avoid using these explicit rotations, and this is and when I say that, I don't mean just I mean both in complexity theoretic sense and also in practical sense. So you do get a better scaling, like asymptotically, and also in practice, the gate. If you look at the gate counts, these other approaches that avoid using rotations, they tend to do better. So Feynman used to say that just mimic nature, but I think now the state of the algorithms try not to mimic nature in a very direct way.
Okay, that's good to know.
Okay. All right. So I guess that is it. So I guess yeah, this is a bit shorter than I expected. The summary is that okay, the 1 and 2 qubit gates are universal, and when you look at the papers, you see that the gates that people use are the Clifford gates plus non-Clifford gates, or the non-Clifford gates are T gates or Toffoli. And this is because we are envisioning using an error-corrected quantum computer. And once you accept that this is the necessity, then there's really a big difference between the cost of the Clifford and non-Clifford and arbitrary rotation gates. So those are the things that I want to emphasize. And okay, so today what I wanted to talk about is this the basic background to set up what we're going to discuss in the remaining lectures. And in the remaining lectures, I will actually talk about what kind of algorithms will be used in quantum simulation, and I'll explain the key ideas. I guess since I have time, we can take some time to ask questions.
Okay, all questions are welcome at this time.
Okay, I have questions. Maybe this is not very much relevant to the real problem of quantum computing and also this lecture, but just out of curiosity, so quantum computing is basically calculation of quantum system, and in real world, or in more specifically in quantum condensed matter physics, we are mostly with the fermionic system. So my question is, this qubit and the qubit algorithm and so on can be applied in general to this many-body fermionic system, or that problem is just out of scope from quantum computing or quantum algorithm? So,
right. So that's actually the biggest. People think that will be the biggest application, and the short answer is yes. So basically, so the way people do is that people just apply the Jordan-Wigner transformation, and of course that leaves this Jordan-Wigner string, which is a very non-local operator. But when it comes down to quantum simulation, this Jordan-Wigner string, it looks like something like this, if I remember correctly. So you have a string of this in the middle, and at the end you have sigma x or sigma y or something. And at the end of the day, you just need to exponentiate operators like this for time evolution, and that is doable, because at the end of the day, this is just a Pauli product operator, and you can map that into a single qubit operator by conjugating by a Clifford, and Cliffords are cheap operations. So in that sense, yes, this problem can be dealt with.
okay, so at best, you can apply this currently developed quantum algorithm only in the one-dimensional fermionic system using this Jordan-Wigner transformation. Am I right?
Oh no, no, because you are still applying to, like, you're using Jordan-Wigner transformation in a not very smart way. So after you do the Jordan-Wigner transformation, you will have a non-local Hamiltonian, obviously, if you have this Hamiltonian in like 2D, 3D, or like Coulomb interaction. But you just directly simulate that non-local Hamiltonian on a quantum computer. And I'm saying that's the non-locality is actually,
I see.
Okay, because you're just exponentiating this.
Okay, so in principle, it's possible to simulate or calculate a fermionic system. In principle.
Yes. Yeah. But it's not, the cost ends up being not good. So like for example, pair cost, the qubits that you need would be similar. The number of time steps you need would be pretty similar.
Okay, thank you.
아까 최영선 교수님 질문 있었던 것 같은데요.
네, 저 아까 마지막 부분에서 한정훈 교수님 질문에 약간 팔로우업 질문인데요. 그러니까 유니터리 오퍼레이터들을 그냥 수학적으로 그냥 2x2 매트릭스로 쓰면 되지만, 실험에서는 저는 항상 이게 결국은 블록스피어에서 로테이션을 해야 된다라고 이해를 했는데, 아까 마지막에 말씀하신 걸 보면은 로테이션을 하지 않고도 트랜스포메이션을 할 수 있다라고 말씀하신 것 같은데 그게 제가 정확히 이해가 안 되는데 혹시 뭐 예를 하나만 들어주실 수 있으신가요?
네. 예를 녹화되니까 영어로 한번 바꿀게요. 그러니까 the question was, so I said the state of the algorithms, they don't really apply rotations directly, but they use other techniques. And so what would be an example of that? So let's say I want to implement this operation. So right. So, okay. So let's say X is an n-bit number. And it represents a fraction. So let's say X is 1, 1. You view it as 0.11 in the binary representation. So that would be 0.75 or something. Okay. And what the goal is to implement e to the I theta x x. And here x is really viewing x as a real number in the binary approximation. So one way to do that is to, well, okay, so what do people do? So in this case, what you would do is something like this. So you begin with x, and what you have is an extra register called QFT. So this is a quantum Fourier transform. You can think of this as a momentum eigenstate. So something like that. And what you do is, yeah, so I forgot the details, but basic, so, okay. Let's say there's no, okay. So there's no theta, then it's simpler. Then then what do you do? So you apply a unitary such that u, x, y is equal to x, y plus x. And this can be done using a very small number of t-gates, which is proportional to the number of bits with a smaller proportionality constant than 3. And if you do this, then what you can verify is that this is okay. So maybe, yeah, yeah. So I messed up some normalization, but basically the point is you can have some ancillary state, so that by using this ancillary state, here the operation that you performed was not actual rotation; it was just an addition, and with that you can effectively generate rotation. So tricks like this exist.
Okay, do we have any other questions? Okay, if not, it's exactly 12 o'clock. And as announced, we will come back on Wednesday, that's 2 days from today, at 10 a.m. with the continuation of his lectures on on the theory of quantum computation. And I hope to see at least as many of you as we did today. And regarding the uploading of videos and lecture notes, probably you will hear announcement from APCTP as they become available, I hope. Okay, so with that, let's thank the speaker for his 2 hours of excellent lecture. And we hope to see him again in 2 days' time. Okay, thank you.
Are we using the same Zoom link for Friday
Oh,
lecture?
yeah. Yeah, please save that Zoom link because you will be we will be using that throughout the entire 12 lecture series.
Okay, thank you.
Okay, thank you. See you all.
Thank you, Doctor.